Color is an element of design. It's an aesthetic, formal element, meaning it's something that actually has form, something we actually work with, that is highly complex. And it is so complex that it does require its own focus of study separate from design theory courses. One of the first things to understand about color is that it is a perception. We see color, but things do not really have color. It is the result of the interaction of light waves hitting our retina and the visual process that goes on in our physiology. The rods and cones receiving the light waves, sending messages down the optic nerve into the vision center of our brain, and so we're looking at something that is red and we recognize it as red as opposed to blue or green or yellow because of these sensations. Color is a property of light. It's a characteristic of light, and without light we cannot see color. So when we develop our study of color, we need to understand that we don't see color without light, but we also need to begin with an understanding of what light is all about as a foundation for understanding color and how to use it. So our first topic is going to be light. Light, if you're aware of physics, is part of the electromagnetic spectrum, so it is energy. It's part of the energy spectrum. In this diagram, you can see that what we see in terms of light is a very small bandwidth in this entire bandwidth of various types of energy, from gamma rays and radio waves. So it's all basically energy. And within this, there's areas of color that we can't really see: ultraviolet light, infrared light. We can't see without the aid of technology. So we have a limited range of understanding of color, of perception of color, but it's still very broad. We can see billions of colors. In the early 1700s, Isaac Newton, who along with a variety of other scientists of the day, were playing around with light and doing experiments and hypotheses about what light and color was all about. And what Isaac figured out was that what we know as white light, that visible spectrum, when refracted through a clear glass device called a prism, the light waves would bend inside the prism, and then as they broke out into the air again, which is another transparent medium, glass is a transparent medium, air is also a transparent medium, the light actually separated into its component colors: red, orange, yellow, green, blue, indigo, and violet. And so all of these mixed together to create the white light. Other hypotheses of the day were that the prism would actually add these colors to the light, but Newton's idea was the correct one, that white light is actually made up of all these colors mixed together. So in the visible light spectrum, we have everything from red on the one end to violet on the other. Over here would be the infrared rays. Over here would be the ultraviolet rays, and we cannot see that with the naked eye. You'll also notice something very interesting is that certain bandwidths of color within the visible light spectrum are wider than others. So yellow is very narrow, the cyan is very narrow. But you can see we start with red and move into red-orange, then we have orange, yellow, yellow-green, into the greens, into the blue-greens, the cyans, the more what we'll call ultramarine blues, and on into blue-violet and then violet. And notice that the widest bandwidths are red, green, and blue. Light emanates from its source in waves, just like ocean waves. Just like with ocean waves, you have some that are taller, some that are shorter, some that are wider, some that are narrower. Red wavelengths are longer than violet light waves. So red light waves will have a greater distance from the top of the wave to the next top of the wave, whereas violet will be a lot shorter. There's a variety of reds, and there's a variety of blues, a variety of greens, there's a variety of indigos and violets. Indigo, by the way, is a blue-violet. That gives us understanding why the different bandwidths are happening. So let's look a little more closely at the anatomy of a light wave. Just like with an ocean wave, the light wave has a height and a depth, and it has a distance. And so the height and the depth will give us the amount of light, So that would be the amplitude. And then the distance gives us the actual color that we're seeing. And so here we have different wavelengths of the same amplitude, the same height, but different wavelengths. So here's a long wavelength and here's a really short wavelength. So you can see that the frequency will increase. The height to width ratio is very important, as well as the number of waves within a bandwidth. And here's an illustrated comparison using the nanometer length of the wavelength. So we have the indigo and the violet, and we have the red on the longest. And these would all be the same amplitude, but this gives you kind of a color version and a direct comparison of the different wavelengths. Light mixes additively. The various component colors mix together to create the full component of light. So we call that white light. And when we do mix the red, the green, and the blue, we get secondary hues known as yellow, magenta, and cyan. But when you mix them all together, you get white light. And this is a basic color chart for understanding wavelength frequency and where things fit within the bandwidth spectrum. And this would be just basically a color wheel where we have the three dominant colors, the three widest bandwidth colors, red, green, and blue, mixing to secondaries and then mixing all together into white light. There are two different types of light sources, and we interact with both types every single day, every moment of every day in our waking hours. Direct light comes from an original source. It's where light is created. So that would be sunlight, could be candlelight, flashlight, car headlight, compact fluorescent bulbs. It's something that actually creates the light. Indirect light is that which is reflected from a surface. We have to have both in order to be able to see. You can't see a surface unless you have the original source, and if you turn out all the lights, you can't see anything and you'll run into things. So you need light to be able to see what's in front of you. When you have light, you can't see a light wave. You can only notice light if you're looking at the direct source or if you're looking at a surface. You cannot see light waves. When light is reflected from a surface, depending upon what the surface is doing, there's going to be various colors that we perceive on that surface. And those various colors will be known as object or local or body colors. So we can say local color, we can say body color, or we can say object color. So in other words, if we're looking here at this shot of the Getty, the sky is basically blue. That's its local or object color. The marble stone wall is, in this photo, kind of gray. There's some foliage here that is slightly green. Because of the diffusion of the light and the time of day, we're not getting bright, vivid colors, but we still see color. The grays that we see, the subdued greens, the subdued blues, and even the blacks in this photo are object colors. Direct light, as we've already mentioned, is light that's created at an original source. And there are actually two types of direct light, one being incandescent and one being luminescent. Incandescent light is that which comes from sources that burn. So your gas flame, light bulb, candlelight, sunlight, firelight, all of these things are things that burn and therefore create light. And things that burn and create light will be cooler looking, so they will be bluer where they are hotter, and then cooler where they're actually looking warmer. So it's kind of an opposition. We think of like reds and oranges as warm colors and blues as cool colors, but with light it's kind of the reverse. The higher the temperature of the light, the bluer it becomes. Indirect light reflected from a surface is the result of pigment, and pigment is a substance that reflects and absorbs light waves. Pigment we often refer to when we're talking about paints and other sort of artistic and design colorants, but pigment is actually anything that will reflect and absorb light waves. So there's pigment, of course, in paint, there's pigment in crayons, there's pigment in food, there's pigment in your skin. Anything that has a perception of color involved will have pigment. There are some things that are not pigmented, and we'll talk about those and what light does with those. So we've got direct light from an original source coming in the form of incandescent light, luminescent light, which I'll continue with in a moment. Then we have indirect light, which is reflected light, and it's reflected because of pigment in the surface. So ultimately, it's all about light, whether direct or reflected. Luminescent light sources are of three types. There's chemical, such as fluorescent light, compact fluorescent bulbs. There's electronic is LED, computer displays, and then there's biological. Plankton, fireflies, anything that will actually generate some sort of glow or some sort of light because of a biological characteristic. Those are luminescent light sources. Luminescent light sources will have a cool light quality, whereas incandescent will tend to have a warm light quality. Not too long ago, in the days of slide film, Kodachrome, Ektachrome, if you took a photograph indoors under incandescent light, it would have, the entire photo would have this warm kind of orangey, red-orange feel to it. If you took a photo under a luminescent light source, it would have an overall cool light quality to it. And then something outdoors, especially toward noon or midday, would have a balanced sense. So the color would be much more accurate and be seen as like real light or daylight. With recent advances in technology with artificial light, you can purchase incandescent light that has a daylight quality to it. You can purchase fluorescent light bulbs that have a more warm or daylight quality. And that's basically because of the filtering that has been placed on the bulb itself. It's not how the light is actually created or generated. It is basically how it's filtered through the coating. LED lights will be balanced. They're a really good alternative to compact fluorescence. Reflected light from a surface, the surface is going to make a big difference in how color is perceived as well. So here's a quick overview about what pigment does in terms of reflection and absorption before we go on into surface quality. If we have white light and its component hues, just using red, green, and blue, it streams from the light source, it hits the surface. If all those colors are being reflected by the pigment back to you at a high luminance, or there's a lot of light being sent back, equal amounts of green, blue, and red, you're going to see white. If you have from the same light source red, green, and blue, and the pigment is deciding to absorb the green and the red, and only blue is kicking back, you're going to see blue. If there's a lot of light being reflected back, it'll be a light blue. If there's very little light, it will be a navy blue. If we're seeing yellow, what's happening is that blue is being absorbed and the red and green are kicking back, and those are recombining into yellow. So that will give us the perception of yellow on that surface. If we're seeing black, most everything is being absorbed across the spectrum and very little is being kicked back. One of the things about black is that when we're dealing with a pigmented surface, you never get true black. True black only exists when you're dealing with light and you take away all the light. So you have to be inside a box that doesn't have any light coming through it, or in an underground cave. True black is absolutely no light. With pigment, we can always take a black surface, no matter how dark it is, cast a shadow on it, in other words, block light, and therefore make it blacker. So in pigment, we don't really ever have a true black. True black only exists where you have no light. There's always going to be some reflection of light off a black surface because pigment does not reflect and absorb perfectly. It will not totally absorb all light. If the surface we're seeing is magenta, which is kind of a cool red, the green part of the spectrum will be absorbed and the blue and red will be bounced back, and they will combine into magenta. And if we're seeing orange, we will have the blue part of the spectrum absorbed and the red and green bounce back, but we'll have more red, we'll have a higher amplitude of red than green. And so the predominance of red in that mixture will give us orange rather than yellow. So if the green and the red are kicking back at equal amplitudes, equal amounts of luminance, we'll see yellow. If the green is less than the red, we'll see orange. If the red happens to be less than the green, we're going to be looking at a yellow-green. Color understanding, color perception is the result of the direct light quality. Do we have cool or warm or balanced light? The surface, is it rough or is it smooth? And then what the pigments themselves are doing. So another issue to deal with is surface quality, also known as texture. When light hits a smooth surface, as shall we say a coated paper or a glossy tabletop, light waves will hit that surface and be reflected off in a parallel manner, and they will compound so that your angle of incident is going to equal your angle of reflection. That's kind of a scientific way of saying if it's going to hit at 45 degrees, it'll bounce off at 45 degrees, and then with a smooth surface, everything is going to be uniform in terms of angle. It's like if you bounce a ball on a floor, it's going to hit and then bounce off away from you at a corresponding angle, meaning at the same angle, but just in the opposite direction. When we have light that's hitting and bouncing off at the same angle, it compounds, and the visual effect, what we see is increased intensity or increased brilliance or saturation or strength of color. If our surface is rough, light waves do not bounce off uniformly. They bounce off in all different directions. They will hit uniformly, but because of the different angles in that surface, they're going to bounce off according to how that angle sends them. It would be the difference between bouncing the ball on a smooth floor and bouncing the ball on a grassy outfield. The ball can bounce just kind of any direction. So when light is scattered, the angle of incident does not equal the angle of reflection. You have decreased intensity. Things can look washed out or pale or kind of tinted. So surface quality, the texture of the paper itself, the texture of the surface itself, is very important for how color is perceived. Another issue about surface quality is just the physical makeup of the surface itself. Whether a surface is opaque or transparent or translucent. Opaque surfaces have opacity, they are solid. Every surface within this water bottle is pigmented. We have the black pigment in certain parts, and we have the grayish pigment and the metallic surface in this thermos bottle to give us a sense of black and gray or black and silver. We cannot see through it. Light does not pass through this, it is only reflected and absorbed. So with opaque surfaces, they contain pigment, and light is reflected and absorbed. With a transparent surface, something that appears clear, such as the body of this bottle, there is no pigment, so there's nothing to reflect and absorb light. With a clear surface, a transparent surface, light transmits, it passes through, it travels through, and there is no sense of color within that surface. It's clear. Compare that to a translucent surface such as this. We can see through this, but there's also color. So light transmits through the surface, but there's also reflection and absorption, and we know that because there is color on that surface. So unless the surface is absolutely clear, there is pigment. Sunglasses and tinted windows do this. They are translucent. We know this as semi-clear or semi-opaque, whichever way you want to phrase it. So there is pigment that's reflecting and absorbing. And obviously here the light that would be absorbed would be the red and the yellow, so we're kicking back blue. We can also see through it, so there's some transmission or movement of light actually through the surface. This is not opaque, this is not solid. Depending upon the surface, light is going to act differently. When we study color in a systematic way. And a system is kind of a logical ordering of things. There are two color systems that we deal with as designers. One is additive and the other is subtractive. Additive color, the additive color system deals with light. The subtractive system, which we'll pick up in Lecture 2, deals with pigment. So additive color deals with direct light. The subtractive will deal with pigments and colorants. And you can't have the subtractive without first having the additive, because without light you can't see color. We need to take a look at the additive color system as an umbrella system, basically to understand what's going on when you're actually looking at a computer display. So this is the world of additive color. We've already seen this device, this kind of color wheel, where we have the three hues and then the secondary hues, and they all mix together into white light. Since it all adds up to white, this is why it's called the additive system. The component colors mix together to create the full idea or the fullness of light. Within each system that we talk about, we will be talking about hues and primaries and secondaries. Hue is a color family. Within the additive color system, our primaries are red, blue, and green. Remember that these are the widest bandwidths. We have the red, we have the green, and we have the blue. So those bandwidths are the primaries, those wide bandwidths. Where they start mixing, blending together, so the green and the blue bandwidth will create cyan, which is a very warm blue, and the green and the red will create yellow. Notice where yellow sits between the green and the red. Yellow is a secondary hue. And then red and blue make magenta, which won't find here because blue is here and red is here. But if you take this component and put them together here, they will create magenta. So we have cyan, magenta, and yellow as additive light secondaries. They are hues, they are secondary hues. So cyan is a secondary hue, means it's mixed from two primaries, and it's a mixture of blue and green light. Magenta is a mixture of red and blue light, and yellow, kind of crazy as it seems, is a mixture of red and green. And basically understanding where things lie in this spectrum. One of the things also about light and color is it really exists in a linear path or a spectrum of color that follows in a logical order. So the idea of a color wheel helps us to study and organize and use color. Each color system that we deal with, additive or subtractive, has properties. And the properties of the additive color system are hue, luminance, and saturation. Hue is the color family or the sense of chroma. As we look at these color pickers from Photoshop, we notice that there's a high degree of chroma up here in the upper right hand corner, and we can go darker and lose chroma. We can go diagonally in each and lose chroma, and we can go horizontally and lose chroma. So we recognize in here a variety of reds, a variety of blues, and a variety of greens. And everywhere you put your cursor, your little eyedropper in this field of color is going to give you a different green. Luminance is the amount of light. In these color pickers, it's most luminant at the top. Luminance corresponds, remember, to the height of the wave, the distance from the trough, which is the lowest point of the wave, to the crest. Low luminance, you have a very short wave in terms of its vertical height. High luminance, you have a lot of light, you've got a lot of height on that wave. And then saturation. Again, highly saturated up here in the upper right corner, no saturation down in the lower left corner. Some saturation, less saturation, a lot less saturation, a lot more saturation. So saturation is basically the purity of the color. In light, reducing the number of light waves within a bandwidth will give you greater saturation. White light is not pure light. Once you separate the various component colors and you take one of those bandwidths, you have more pure light. If you take just one wavelength within a bandwidth, say wavelength 700 nanometers, that would be pure light. Laser light is a single wavelength of light that is compounded on itself over and over again to really increase the amount of energy that is being given off. And that's what makes laser so powerful. So laser at this point is about the purest light that we know. White light is not pure. If you can isolate to a single wavelength, you have ultimately pure light. The additive color system deals with your cell phone, computers, televisions, digital cameras, analog cameras, lights, stage lighting, and so as designers, since we now get to work with computers, we're dealing with the additive system on a daily basis. The disciplines that engage in the additive color system include web design, basic graphic design, photography, interior architecture, film, video, motion graphics, animation, anything that is displayed on a computer display deals with light. So additive is all around us, and as designers we need to understand the additive and its relationship to the subtractive in order to start understanding what color is all about and how to use it as designers.